Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be going through section 2.2, Organizing Quantitative Data. This is going to be moving on from 2.1, where we organize qualitative data using bar graphs, frequency distributions, and pie charts. Here we're going to be talking about how to organize quantitative data, data that comes in and is treated in the numerical sense. You'll also note that on the side here I have my TI calculator presented. The reason is because we are going to be working with some data sets here, and I want to show you some nice quick ways to do some of our calculations. The data sets that I have here, I have in L1. Well, first, if you don't know how to get here, I'll show you. You can go to Stat. This is where we're going to do our statistics. And then the first option you see on the screen says edit ... That's going to allow us to edit our data sets or our lists. So I'm going to go into edit, and you should see your list here. Now, if you happen to have anything in your lists, like for example, I'll just put in a couple numbers here. If you have a couple numbers in the list, what you can do is go to each of them and clear them out. Or what I recommend doing is going to the top. So scrolling to the top until you see that you have whatever list you want highlighted. You'll even see on the screen here below it says L2 equals for me, or whatever list you have equals. Instead of each individual point would say L2 parentheses 1. You would want the entire list highlighted. And when you have the hit list, what you can do is hit clear on the list. Clear, not delete. Hit clear, which is right below the arrow keys, and hit enter to clear out everything in the list. You could do that, and then what I have here are lists that we're going to use. I have a list on the second page here, which is page 6. Page 6, there's numbers 7, 13, 7, etc. I have those in list 1. So all you would need to do is go to, say I'll show you how to do that in list 2. You could type in 7, 13, enter, 7, enter, 8, enter, 5, enter. So you can put each of these in by simply typing the number and then hitting enter, and that will enter it into your list. So I'm going to clear that out. The list that I have the one here on page 6. I have the number 7, 13, 7, etc. I have the table on page 7. I have the numbers 16, 18, 12, 3, and 1. I have that in list 3. I'm keeping list 2 and list 4 intentionally blank. And then list 5 is the table in page 7 here for grams of fat McDonald's breakfast. I have that in all of list 5. And then list 6, I have the table, I guess I was on page 8. I have the table on page 9 then, the number of arrivals at Wendy's. I have those on list 6. If you want to get those done before the video continues, or you want to get them done as they come up, however you want, I recommend having those in though so you can practice how to work with your calculator, because you are going to use that a lot in this class. Okay, but before we get into that, we have a couple definitions. The first type of way that we're going to represent the qualitative data, the thing that we talked about before, was with bar graphs. However, with quantitative data, we're going to use what are called histograms, which are going to look very, very similar, but they're for discrete quantitative data or continuous quantitative data. And it's going to put the data into classes. Before, when we had bar graphs, the data were more or less already in classes. They were in categories, and we simply had how frequent each category showed up. For histograms, it's not going to work as nicely, particularly if you have continuous data. If I have data that doesn't repeat too often, it's very hard to work with. These classes that we set up are instead going to represent a multitude of numbers. It's going to represent a range of numbers. These classes will also have equal widths. You see that it says bars have equal widths. Bars are the same thing as classes, so data is grouped into classes or bars. You'll hear me use these words interchangeably. And the other difference between histograms is that bars are touching. This is why I was very clear with bar graphs that you do not have the bars touching. That is a different type of graph. We will call the lower class limit the smallest value in a class, and the upper class limit the largest value in a class. And more importantly, the class width, which is a very common thing to either calculate or work with, is going to be the difference between consecutive lower class limits. Note that is not the difference between the lower class and the upper class limits. It's the difference between consecutive lower class limits. So whatever the lowest class is, the lowest number is on a class, minus the next lowest number on the next class, that's going to be your class width. We will call an open-ended graph a graph where the ends of the graph, the last bar or the first bar, go on for infinity. So the first class has no lower limit and the last class has no upper limit. You will very seldom ever see open-ended actual histograms created, at least for the time being. Some examples of histograms are as follows. This is what we mean by classes and class widths. If I look at this second graph, this is a very typical representation of a histogram. You see that here all the bars or classes are touching each other. Furthermore, they all have the same width. This first bar goes from 0 to 5, and then 5 to 10, 10 to 15, 15 to 20. That means each of these has a class width of 5. That's how wide each of the classes are. As I said, the bars are touching each other, so that's another important key piece. But now also notice that we've lost some information compared to when we were working with bar graphs. This middle bar that represents 20 to 25, well, I can see the frequency of it. I see the frequency goes up to about 55. We read that the same way that we did for bar graphs. The unfortunate thing is I don't know what those numbers were anymore originally. I don't know if that was maybe 50 numbers that were 21 and then 5 numbers that were not 21, that were somewhere between 20 and 25. Or maybe I had an even split between all those values. I'm not exactly sure. That's the unfortunate thing about histograms, is that when you make it, you do end up losing some information because the data is grouped together into these classes. All right, but we'll get into more of that. You'll see what I mean in just a bit. For the shape of the distribution, we are generally going to be able to talk about the shape of the distribution. That way we can tell somebody what the distribution looks like without even presenting a picture. If we say something is uniform, that means that all the classes are roughly the same height or the same frequency. If you notice, that also means that this graph is symmetric, which means the left side, it looks the same as the right side does on the graph itself. But we say something is relatively uniform if it has this more or less plateau shape. If it's a little bit off, maybe one of these bars is a little bit higher than the other. So maybe this first bar is a little bit higher. This bar here is a little bit lower, so that top part doesn't exist. We can still say it's relatively uniform. It doesn't have to be perfect. The most common shape that you'll see, particularly in this entire class, is what we call a bell-shaped graph. This means that the values in the middle here are very common. They have very high frequencies compared to the values on the sides of the graph. The values on the high end are very low, and the values on the low end are very low. That's why it makes this bell type of shape. If I were to make a curve over this graph, this kind of looks like a bell. It is also relatively symmetric. If I were to cut it directly in half, then the left side looks approximately the same as the right side. Now, it doesn't look perfect. This bar is a little bit taller than this bar, so it's not exactly perfectly symmetric, but that's what we mean by symmetric. It's relatively. If it's not uniform or bell-shaped, the two symmetric type of graphs, we usually say that it is either skewed right or skewed left. The skew in this case is indicating that the graph is not symmetric, and in this case it tapers off in that direction. Skewing right in this graph means that if I start at the top of the graph and I go down to the right, I get the longer tail going down to the right side. Whereas if I say it's skewing left, I start at the top point of the graph, and if I go to the left side, that's the tail that extends further. So that's what you want to look for the direction of skew. Which tail extends further? Sometimes I even say that this looks like a mouse or a rat. So you have a mouse, maybe it has a nose, it's got ears, it's got the body here in the middle, but then the tail of the mouse is over here. So whichever side the tail is, that's the direction of the skew. Sometimes I also say, if you imagine this like a ski slope on a mountain, which direction would be the easier side to go? Well, if I look at this fourth graph here, the skewed left graph, if I start at the top of the mountain, and if I go to the left, that's a much easier slope to go down if I were skiing or snowboarding than it would be to go down this right side, which looks a lot more steep. So there's a couple ways to try to remember skew. There are other types of shapes of graphs as well. Obviously, like these aren't the only graphs that you will see, but these are the general ones that we tend to see. Another common one is something called a bimodal graph. A bimodal graph looks something like this, where you have one peak and then another peak somewhere else. Whether they're the same height or not, that would be what we call a bimodal graph, because it has two modes here, or it has two bars that are really, really high. Sometimes those show up, but not as often as the ones we're dealing with here. Usually we'll say it's either bell-shaped, uniform, or skewed either right or left. Describing the shape is really good because then you can just tell the reader what the data looks like, and if I tell you the data looks skewed right, then you can have an idea in your head already of what the data looks like without even seeing a picture. Okay, so we have a couple examples of working with these. First, we have cigarette tax rates. The table shows the tax in dollars on a pack of cigarettes in each of the 50 states and Washington, D.C. as of January 2014, even though January is a little bit spelled wrong. So we have 51 pieces of data because we have 50 states and Washington, so 51 pieces of data. The data is presented here in this little table. Construct a relative frequency distribution with a lower class limit of 0 and a class width of 0.5. That is what is presented here. In this case, a relative frequency distribution is already presented to you. The classes are here in the tax section. You see the first class goes from 0 to 0.49. The next one starts at 0.5 up to 0.99. The class width they gave us is what is telling us the difference between the consecutive lower classes are. The first class has a lower class limit of 0. The second class has a lower class limit of 0.5. The next class goes to 1, and then 1.5, 2, 2.5, 3. That's what we would be working with if we were constructing class widths. Then, the upper class limits that we tend to write, there's a couple different ways of doing this depending on the statistician you talk to, but generally you will make the upper class limit the number directly before the next lower class. So if you see 0 up to 0.5, that means the previous upper class would be 0.49. Likewise, the next lower class was 1, so we would make the previous upper class 0.99. And then 1.49, 1.99, you tend to see a general pattern when you're drawing these or creating them. Some statisticians instead do it in a different way with lower and upper classes. Some would do it in the way of 0 to 0.50, and then 0.50 to 0 or 1.0. And then 1.00 to 1.50. This is sometimes how relative frequencies and classes are created. The problem with this, the difficulty, is that if you notice, 0.50 shows up both as an upper class and a lower class. So the question would be, if the number 0.50 showed up in this little table, would I put that in the first class or in the second class, or both? Well, the answer should be the second class. You should always include the lower class limits. the upper class limits are never really included in this way, which is why we very often will instead present it as 0 to 0.49 instead. Although really, 0 to 0.49 really means 0 to 0.499999. It really means 0 up to 0.5, but not including 0.5. So, a couple different ways of working with class limits depending who you talk to. So if you look up some things about creating histograms, sometimes you'll see class limits presented in a little bit of a different way. When you have your classes done, then what we're going to do is go through that table and count how many values do I have in each of those classes. So for 0 to 0.49, what I would do is look at this table and say, how many numbers do I have between 0 and 0.49? For example, I have 0.425 is between 0 and 0.49. I have 0.37. I have, let's see what else I have, 0.36, 0.17, 0.44, 0.45, 0.30. I have quite a few numbers. I think that actually is it. Yeah. So those numbers would be the ones between 0 and 0.49. Therefore, I have a frequency of 7. There are 7 numbers between 0 and 0.49. Likewise, I can do the same thing for every single other class. So between 0.5 and 1, I can find the frequency for all those. In this case, it's already done because we just wanted to work through this one and just first talk about creating the frequencies and then making the graph for that. So the frequencies are already done here. All we need to fill in, though, are the relative frequencies. Okay. Now, I have the calculator up on the side, and I have the numbers 7, 13, 7, 8, etc. All those numbers represented in the calculator in list 1. Now what I'm going to do a little bit of list manipulation. I have a video up for this on my channel as well for list manipulation. If you go to my channel and look for the calculator tutorials, you'll see that. But I'm also going to show how to do that here. What I'm going to do is I'm going to take all these values, these frequency values, and I want to make relative frequencies. Well, in order to do that, as we talked about in 2.1, I want to take every frequency value and I want to divide by the total. The total in this case is 50 states and Washington, D.C., so 51. Therefore, I want to take 7 divided by 51, 13 divided by 51, 7 divided by 51. I want to do all these frequencies divided by 51, which is a little bit slow, and the bigger the table becomes, the more annoying it becomes. What I can instead do is manipulate that entire first list L1 and create the relative frequencies all at once. To do that, I'm going to go into L2 as I have here, and I'm going to hit up so that I'm highlighting the entire list. So you'll see now on my screen it says L2 equals right below the table list. If you see L2 parentheses anything, that means you're not in the right place. Make sure you scroll up. This way I'm going to adjust the entire list too. I'm going to fill in that list too with my relative frequencies. To do so, I want to take all the values from L1. In order to do that, I'm going to do second, so the second button, which is in the top corner, and then I'm going to hit the number 1. If you see on my calculator above the number 1 in blue, it says L1. That's corresponding to the button second. I believe on TI-83s it is in orange or yellow. This second button is going to work like a shift key on your calculator. So hitting second and then 1 will access the secondary option above the number 1. So now my screen says L2 equals L1. What I want to do is take all the numbers from L1 and divide by 51. So I'm simply going to hit division, so divide by 51. So now it should say L2 equals L1 divided by 51. That's all I need. If I hit enter on that, it then should populate list 2 with all of the relative frequencies. These are all the values of 7 divided by 51, 13 divided by 51, etc. So all the relative frequencies are filled out. So I'm going to fill those out real quick here. I'll just do 2 decimal places to make it easier. So 0.14 looks like 0.25, another 0.14, 0.16, 0.10, 0.10, 0.06, 0.04, and 0.02. All right. Now, these decimals, I think if you add them all up, I highly doubt they add up to exactly 1 because every single one of them rounded up, but you'll see. They may round up to 1. It all depends, or maybe just a little bit less. But these are the relative frequencies we're going to work with. With those relative frequencies, I can create a table here, and we're going to create this histogram, We're going to create this histogram using those relative frequencies, and we're going to create it similar to how we do with a bar graph, but remember, these histograms will have classes where the classes touch, and they represent values between given numbers. The first class, according to my table, was 0 to 0.49, and that has a relative frequency of 0.14. So 0 up to 0.49, or really up to 0.5, and that had a relative frequency of 0.14, so around there. I'm going to make my bars always go from one lower class to the next lower class, just like the class widths should be. So the next lower class goes from 0.5 and ends on 1. That one has a relative frequency of 0.25 we calculated. So 0.25 is roughly here. Notice how I drew these bars so that one bar started and then the next bar started from that. So they're always touching each other. You should only ever have a space between bars if there's an empty class. Sometimes that happens where a class has 0 entries and then you would just have no bar for that. Sometimes that happens, but it's kind of rare. All right. Next one we have is another 0.14, which would be same place as the last one. Then 0.16, so a little bit higher. Then 0.10 for a couple of them. So this one goes to 0.10, and so does the next one. Then 0.6 is right there. 0.4 and 0.2. This would be the histogram that we would create. There is kind of an empty class here, at least on the table or on the histogram. You see 0.4 or 4.5 up to 5. I don't have that class here at all. There are no values between those, so it's an empty class. There's nothing there. Now the question ends there in terms of creating the histogram, but we have a couple other things to address since we've created the distribution and the histogram. What percentage of states have $3 or more in tax on, or $3 or more in tax on a pack of cigarettes? Well, $3 or more, that means that we're looking at the end few values. So looking at my distribution here, I'm looking at these three. This would be $3 or more, so that's 6, 4, and 2. That adds up to 12%. Because that's 6 plus 4 plus 2 gave me 12%. And lastly, what is the shape of the distribution? The shape of the distribution, looking at my graph, I see if I were to make a general trend or curve over this, I have a large amount of the values early on, and then it tapers off to the right. That means that this is going to be skewed, and we say that it is skewed right. You can also see that when looking at the distribution. The more you do these, the more you may be able to notice it just looking at the frequency distribution, that I have a lot of values early on and very few later on. So this does look skewed right. Okay, so that's one example. We're going to do another one where we're also going to do some stuff with the tables and the calculator, so you can give this one a shot. Predicting school enrollment. To predict future enrollment in a school district, 50 households within the district were sampled and asked to disclose the number of children under the age of 5 living in the household. The results of the survey are presented here. So we have number of children, 0 through 4, and the number of households. Okay, I have the number of households in L3. If you don't already have that, I recommend doing so to practice the relative frequency we're about to create. First, though, is the data discrete or continuous? If you haven't already, pause the video and try to see if you can give this whole question a shot, see if you can answer it, and then check how you did. For discrete versus continuous, remember discrete means countable. If the possible values are countable versus continuous, where infinite decimals are allowed. So if I can keep adding decimals and it makes sense to a possible reported value, then it would be continuous. Well, the possible reported values for how many children live in a household are 0, 1, 2, 3, 4, or any integer past that. These are countable numbers. I can't have 1.268 children in a house. So we would say that this is discrete because number of children is countable. Let's see if I can type that here. Number of children is countable. So this is discrete. Okay. With that in mind, we can now construct a relative frequency distribution. We have these values here, the frequency values of 16, 18, 12, 3, and 1. And we need to make those relative frequencies by dividing by the total. Well, remember, if the total is not given, you can always sum these up if you want to, but also in the description, it says that there were 50 households, so we know the total is 50. So what I'm going to do, I'm going to go into L4 like I did before, highlight the top of it, make sure I have L4 equals, and then I'm going to do second 3 to grab all the numbers from list 3, where my numbers are, and I'm going to divide L3 by 50. Hit enter and we get our decimal values. I'm going to report my relative frequencies next to the histogram down here. So 0, we have 0.32 for our relative frequency, then 0.36, 0.24, 0.06, and 0.02. So that means A and B are done. With these numbers, we can now create a relative frequency histogram. Notice that our classes look kind of like bars now, but really what this means, if I were to replace these classes, I would say this really means 0 up to 0.99, and then 1 up to 1.99, 2 up to 2.99, 3 up to 3.99, and 4 up to 4.99. Or really 0 up to 1 but not including. And that's how I'm going to represent these relative frequencies. I'm going to start my first bar at 0, and it goes up to 1, and it has a relative frequency of 0.32, which is a little bit above 0.3. Remember, do not make this like a bar graph where the bar is centered around something. Also, when you make the classes, do not label the class, some people do this, don't label the center of the class as 0 to 1 or 0 to 0.99. Don't do that. Do not label the middle of the class. You always are labeling the edges of the class, which represent the lower class limits. Moving on though, 1 to 2 is 0.36, so a little bit above 0.35. 0.24 is around there. 0.06 is around there. And 0.02 is roughly there. You will notice that it was a little bit hard for me to create the bars and make them as tall as I exactly wanted to. Some people like to do these lines that go across the graph itself that can help adjust to make sure that you have the right height. And it's also a lot easier for a reader to see how tall a bar is, because it is a little bit hard to see how tall this bar is by scrolling all the way across. It's very easy to misrepresent that. So we have our relative frequency histogram done. Then a couple of questions. What percentage of households have 2 or more children? Well, 2 or more are these 3 values here. 24% plus 6% is 30, plus 2 is 32%. So 24 plus 6 plus 2. That would be 2 or more children. And then secondly, the shape of the distribution. Well, I have the majority here, and then it tapers off again to the right. So this is, again, skewed right. All right. Next question. Backpack weights. The following frequency distribution histogram represents the weights of a random sample of college students' backpack weights. So the histogram is already created. I will say when you do create histograms, there are a few things that you should have, and this histogram would be missing a few things in my mind. Histogram should always have labels here. So this has a frequency label here, which is nice, but you should have a label here. Maybe this is in pounds. And then an overall title as well, so something like backpack weights. All right, backpack weights. That would be a good title for the graph itself. That represents to the reader what this graph is trying to do. I always say that when you create a graph, you should strive to allow it to be able to stand on its own without any associated paragraph of information. I want this graph, if I were to put this on a separate sheet of paper and drop it on the ground, I want somebody to be able to pick it up and have an idea of what this graph is representing without having this description laying it out for them. So always try to make a graph be able to stand on its own. Okay, so a few questions here. How many students were sampled? Well, it didn't give that to us in the description, but we can find this roughly by trying to find how tall each of these bars are. Now, this is going to be a little different depending on how you read these bars, but your value shouldn't be too far off from what mine is. The first bar is 0 to 5 is about 2-ish, maybe 3. 5 to 10 looks somewhere in the middle between 0 and 10, so 5, I'd say. 10 to 15 goes up to maybe 22. 15 to 20 goes up to 50, looks like exactly. 20 to 25 looks up to 55. 25 to 30 goes up to maybe 45 or 46. I'll say 46 this time. Looks like it goes a little bit higher. Then 30 to 35 goes up to maybe 19. 35 to 40 goes up to, it's not 5, maybe 3 or 4. I'll say 3. And then lastly, 40 to 45 looks like 0 to 5, which I said 2 before, so I'll say 2. If I add all these values together, 2 plus 5 plus 22 plus 50 plus 55 plus 46 plus 19 plus 3 plus 2, I get about 204. Now, this could change depending on how you read the bars. Maybe you read one of them as one higher or one less than mine, so maybe you get something around, like probably around 200 to 206 would probably be okay, depending on how you read these numbers. But it should be close to that. One number that is more definitive, though, is the class width. The class width is how wide each class is. First class goes from 0 to 5, 5 to 10, 10 to 15. Each of these has a width of 5. 0 to 5, 5 to 10. Subtracting each of those lower class limits should give me a difference of 5. 35 and 40. 40 minus 35 is 5. The most common weight I see here, I don't have a singular weight, but I have a class of weights. I have between 20 and 25. So 20 to 25. It doesn't really say pounds or grams. I'm going to assume pounds, though. What percent of students have a backpack that weighs at least 30 pounds? Okay, now we know it's pounds. At least 30 pounds. Well, at least 30 pounds means 30 pounds or more. So that means we're looking at this region of the graph. And to keep consistent, those are the last 3 numbers we used in part A. So 19 plus 3 plus 2. That gives me 24 of the values. And that's 24 out of 204. If I do 24 out of 204, I get about 11.7%, or I'll say just a nice clean 12%. It doesn't say how to round, so I can just keep it as a whole number there. Lastly, what is the shape of the distribution? Looking at the entire distribution itself, this definitely follows a nice bell trend. So we'll say bell-shaped distribution. It's better to say bell-shaped distribution here than symmetric, because symmetric could mean what we have here, or if you recall, symmetric could also mean this kind of graph, because this is also a symmetric graph, but that's not what we want. We want specifically a bell-shaped graph. If you say bell-shaped parentheses symmetric, that's fine. And later on in the class, there will actually be another word that we use to represent this kind of graph, because again, this is a very important shape. All right, so those are a couple examples of the primary way of representing quantitative data, with relative frequencies like we did before, but also with histograms. Histograms are the primary way of representing quantitative data. Now, that's not the only way. There are a couple more small kind of graphs, but these are really just different types of histograms. First, we have a stem and leaf plot. It's another way of representing quantitative data. You may have seen these before, but these are ways of organizing the data in a kind of distribution, kind of graph format. It's basically a mix between a distribution and a histogram. In order to do a stem and leaf plot, what we're going to do is we're going to make a two table here where we have the stems and the leaves. The stems in your stem and leaf plot will represent the leftmost digits. So in this case, if I look at these numbers I have here, 12, 22, 27, 3, 30, I have a lot of numbers like this. The leftmost digit here are the tens digits. So my stems are going to represent the tens. So I have 0 because I have some that don't have any tens, like 3 and 9. I have 10s, 20s, 30s, 40s, 50s, and I don't think I see any 60s, but if I do find some, I can always fix that. The leaves are going to represent the rightmost digits on these. So, for example, 12, I'm going to represent that by putting a 2 as a leaf off of the stem of 1. That way, if I combine any stem with a leaf, 1 and 2 make the number 12. 27 I can have represented next to the stem of 2. That can represent the number 27. That's how the stem and leaf plot is going to work. However, you also want the whole stem and leaf plot itself to be in numerical order. And the table that I have here is not in numerical order. What I'm going to do is show you how to change the entire list that you have in your calculator to be in numerical order, which is a nice and convenient thing to know. So I have this table in list 5 right now, 12, 22, 27, 3, etc. All the numbers here are in list 5. What I'm going to do now is I'm going to sort this list. In order to do that, I'm going to hit stat again, just like if we were going to go into the list. And if you see below edit, there are two options, sort A and sort D. Sort A means sort in ascending order, which means in increasing order. Sort D means descending order, so sort in decreasing order. I'm going to sort ascending, so I'm going to do sort A, which is going to paste this function to the main screen. Now, do you see the cursor after that, which is asking for what list? Well, I want it to sort list 5, so I'm going to do second 5, and the parentheses, and I'm going to hit enter, and it should just simply say done. It should take less than a second to do. It's a very easy operation for the calculator to do. Now, if I go into stats and edit to view my lists, I should now see that list 5 is in ascending order. So then I can use that list to help make my life easier for stem and leaf plots, and also the next plot we make. For stem and leaf plots, I have 0, I have 3, and 9. So my leaves I'm going to represent as 3 and also 9. Some stem and leaf plots don't use commas between digits. I recommend doing it. It's a lot easier to separate. But what you do always want to make sure is that the spacing between the digits is uniform. So if I have multiple digits here, I'm not going to try to squish them all together. I'm going to try to keep the spacing the same, and you'll see why in a moment. For tens, I have 11, 12, and 2 16s. So I have 11, I have a 12, I have a 16, and I have another 16. Yes, I am going to represent both versions of 16 as their individual digits. For 20s, I have 21, 22, 22, 24, 25. So I have quite a few 20s. I'm going to scroll down here to make sure I see all of them. There we go. So I have 21. I have two 22s. I have a 24, 25, and two 27s. So 4, 5, and 2 7s. Notice again, I'm trying to keep the spacing between the numbers the same, as much as I can. Then I continue for the rest of this. You could probably fill out the rest from here, but for 30s, I have quite a few as well. I have two 30s themselves, so 2 zeros. I have a 1, 2 2s, a 6, and a 7. For 40s, I have a single 40 of 46. And I have three 50s. I have a 1, a 5, and a 9. That would be a stem and leaf plot. Not too bad to make overall. And it does represent the data, and it kind of summarizes it down into a smaller, more readable sense. But what it also does, as I said, it mixes histograms. If you think about it, these stems each represent one class. This first class from 0 up to but not including 10. Then 10 up to but not including 20. So each class here has a width of 10. And I can make bars that go to how far these go out. And what I see here now is basically a histogram that's just on its side. So that's what I mean by it mixes a distribution because it lists all the numbers, but it also kind of looks like a histogram itself. Now, it does also ask us to describe the distribution in the question. And looking at this, I do see a majority of the data here in the center, in the 20s and 30s, and then it tapers off in both directions. Not perfectly evenly. If you notice, the 40s is significantly less than the 10s. However, it's not that far off. I would still say something along the lines of that this is relatively bell-shaped, implying that it's not perfectly bell-shaped, but it's close enough. It's not far off. You'll very seldom ever see data that's perfectly bell-shaped. It'll just be close to it. That's how to do a stem and leaf plot. One more type of graph that we have here. We have one more type of graph and then a couple questions with it. We have a dot plot. A dot plot is another graph for quantitative data. That is created by placing a dot above the value for each observation across the horizontal number line in increasing order. So what that means is that here we're going to have this number line, and notice there's no vertical axis here for us to work with. We're going to more or less simulate that. And all we're going to do is count up the occurrences for each of the number of customers. For example, I have a singular 1, and all I'm going to do is represent that with a dot. For every occurrence, I'm going to represent that with multiple dots, just going up in a vertical fashion. So that's what a dot plot is. For this example, we have Wendy's arrival times. The manager at Wendy's fast food restaurant wants to know the typical number of customers who arrive during lunch during the lunch hour. The following data represents the number of customers who arrive at Wendy's for 40 randomly selected 15-minute time intervals during lunch. Construct a dot plot and identify the distribution. Or it really means identify the shape of it. So this table here is horrible. We would not want to give this to a reader and say, okay, figure out yourself what the data really means. We want to present this in a better way. I have this data in list 6 myself, and like before, what I'm going to do is sort this list. So go ahead and give it a shot and sort it yourself to see if you remember how to do it. I'll give you a few seconds. Okay. So what we would do here is take stat. We want to go down into sort A for ascending order. Sorry, mine had a little bit of an issue here. It double hit enter. Sort A, and what we want to do is sort list 6. So not the number 6, we want to do second 6. So we get L6. Or wherever you have the list. So it says done now. If I go into my list, I should be able to look at list 6, and it now is in numerical order. Okay, so looking down into this list, we can count how many values show up. So for example, there's 1, 1, which we already have represented. There's 1, 2, so I'm going to put another dot for 2. There's 1, 3. There are 2 4s, and so since now we have multiple of 4s, what I'm going to do is put 1 dot and then another dot above it. I'm also going to recommend, like before, try to keep spacing as uniform as possible. 5, there's 2 5s. 6s, I have 1, 2, 3, 4 6s. So 1, 2, 3, 4. And what I'm going to do, I'm going to pause the video, and I'm going to fill out the rest of these. Okay, so I have the rest of this filled out. There were 9 7s, there are 12 8s, there were 7 9s, and 1 11. Again, I tried to keep this as consistent as possible in terms of the spaces between dots. But again, it's not the easiest to do when you're drawing. So if it's not perfect, that's fine. But try to keep it as consistent as possible, because we're also going to try to represent the shape of this graph. Notice that these start to make a nice curvature shape. It starts to look again like another histogram. Here, the histogram is really just representing a width of 1. Each singular number is its own class. If I were to make a curve to show the shape of this graph, I'll get something like that. And it looks like, definitely starting from the top, it looks like it is skewing, in this case, to the left more than it is to the right anyway. Also notice a little bit of a weird thing. There is an empty class here. I did say that histograms can have empty classes. If you don't have any values for that, that's perfectly fine. It does happen sometimes. All right, the shape of the distribution, as I already said, this is skewed left. And what proportion or percent of the 15-minute intervals had greater than 7 customers? Well, greater than 7 means more than 7, which means 8, 9, 10, or 11. So that'd be 12 plus 7 plus 0 for 10s plus 1 for 11s. That gives me 20. And out of the total, which there were 40 times according to the description, that gives me 0.50 or 50%. So 50% of the customers were greater than, or 50% of the 15-minute time intervals were greater than 7 customers. So dot plots and Stemleaf plots are both variations of histograms. Just note that they are incredibly limiting. If you have too complex of data, or even if you have continuous data, neither of these are really appropriate. If you have data that spreads too far or too wide, then usually dot plots and Stemleaf plots are not appropriate either. They're really only useful for smaller data sets, like 20 to 40, as these last few were. Smaller data sets that have a limited number of possible values and are discrete. So under very limiting cases, you can use these plots, but generally you can make just a histogram instead to represent the data if necessary. But with that said, that's everything from 2.2, how to represent quantitative data. This was a little bit longer, but that's because quantitative data is a little bit more complicated and also more important for us. We do a lot more with quantitative data, so make sure you get down histograms. But at this point, you should be able to continue and work on the homework for section 2.2, so I recommend working on that before you take a look at section 2.3. But with that said, I hope you have a great day.